Good morning, everyone. This is Sundar Atre, and we are dealing with lecture 5, which is looking at building off from material indices and leveraging that into selecting materials for a given design. For a product, we have said that there's an interaction between the function, the shape, the process, and material. In this lecture, we will look at different aspects of materials that affect design process. In order to select materials, there are four main steps from going from over 160,000 materials, as we had seen, to get down to narrowing the final choice for a given product. The four steps consist of, firstly, translation. So in translation, you identify the key properties that are useful for selecting a material or are important for that design situation. Screening removes ineligible candidates, considers things that are good enough. Ranking then allows you to get to things in terms of material choices that are the best that are there. That's the difference between screening and ranking, and then that process is documented to give further details about the material and the choices for process and things like that. Okay. The focus is on using the material indices that we have defined earlier to get into material selection. In order to do that, we will look at four main steps that we had provided an example for in lecture 3. The first is function. What does the component do? What kind of loads does it bear? Then what are some constraints in the design? How strong should it be? How much load should it take? How stiff should it be? These are kinds of examples. How thermally conductive should it be? That could be another variation. How transparent should it be? So then the objective becomes, what are you doing, right? To be able to sift through multiple options that fit the bill based on constraints alone. And so then the question is, what are you maximizing or minimizing, right, as an optimization situation to get the best outcome? Free variables are those that are not constrained. And so what parameters are you free to change without affecting the overall objective? These are the four steps. Let's take the familiar example of this heat sink that is used in power electronics. So you have a bunch of chips, they generate heat. That heat has to be removed so that the temperature doesn't get too high, right? And so you have a bunch of fins. And so in this sense, the function is it should serve as a good heat sink. Constraints are the material should be a good insulator, or the electrical conductivity should be less than the reciprocal of this, or the electrical resistivity should be greater than 10 power 19 micro ohm centimeter. Suppose dimensions are all specified as well as a constraint, because depending upon the changes in surface area, you would have different heat sink attributes. So then the objective is to maximize the thermal conductivity of the material for a given electrical resistivity constraint. So between that, what is the best material that gives the highest thermal conductivity? So for the selection strategy, we have seen that the design requirements should be expressed as constraints and objectives to deal with those four steps. And the kinds of constraints can be electrical, thermal, CTE, and things like that. Objectives can be to make it as cheap as possible. For instance, it could be making it as light as possible or having the highest operating temperature as possible. So if you go into the database, whether it's a handbook, whether it's talking to people, or going into CES itself, there will be a vast pool of information. In CES, there is a comparison engine available between the design requirements that are expressed and material attributes over a wide range that fit the bill. You can initially screen to look at options that fit the minimum requirements, and then you can rank them based on this optimization or objective consideration of the design. For instance, cheapest as possible by looking at price as a separate attribute. Finally, we document different attributes of the material itself and alternatives that were considered that are close or were discarded because they were not good enough. And so you can justify the final selection. Let's take a look at this chart of thermal conductivity as electrical resistivity as a way in which we address, first of all, the minimum electrical resistivity that's possible, so 10 power 19 micro ohms centimeter. This was a design requirement, so materials to the right of this line are all candidates, and materials to the left of this line are all eliminated. So a good bit of natural materials, composites, foams, and metals are completely eliminated. Then if in addition you maintain a minimum thermal conductivity, let's say about 25 watt per meter Kelvin based on this horizontal line, then only two options are thrown up over here. These include aluminum nitride and alumina, with the silicon nitride being a close possibility lying just on the line based on this quadrant over here. Everything else is discarded through the process. How does this get done computationally? That's one type of a question to address. The second aspect is really, let's take a look at another type of a design problem. You want to select a material for this cable. Right? You have overhead transmission lines, you have underground transmission lines. Increasingly, they tend to be more of overhead transmission lines. These are expensive towers, so you want to be able to maximize the length that you can have and maintain a certain tension without having to put too many towers, because that will affect the cost. Let's say that somehow the length has been specified. Now we have to, from a material side, decide what all this cable can do. What kind of criteria are we looking at? The main criteria we're looking at is, first of all, the electrical conductivity. The other is the kind of strength it can have to not collapse under not only its own weight, but other stresses. What are some kinds of stresses that can be? One can be wind, for instance, right? One can be changes in weather, and so some icing that can happen. But changes in weather can also deal with other possibilities, right? Migrating birds sitting on these things. If there is a lot of them and then they have a fight, the cable cannot collapse. Storms. These are all some possibilities to look at as design considerations that will allow for lesser maintenance and lesser downtime depending upon the region that these towers are located. What does all this mean in terms of the 4 steps of function, constraints, objective, and free variables in order to select the right material? So the function is a long span transmission line. Let's say L is specified. Then depending upon the different loads, let's say the strength is greater than 80 megapascals. The objective is to minimize electrical resistivity, and the free variables are choice of material. So what can you use? Any thoughts? As it turns out, for these types of constraints, if you plot strength versus electrical resistivity, for instance, you will be able to get aluminum and copper as your key possibilities. Give it a try on CES EduPack just to become comfortable with the software.